Hey everyone, my name's Octavia. I'm the principal security engineer here at Prelude. I'm also the community manager. And for those that are new, so we have a lot of new faces in here today. Every week or so, we're inviting guest speakers from the InfoSec community to come out and talk about something. Might be Windows internals, could be how to write a Packer, reverse engineering concepts, whatever. And what I'm trying to do is just build a space where people come out and share their knowledge casually. We have some new and first time speakers that'll be joining us next month. People giving their very first talk, which I'm very excited for. And then we have folks like our guest today who have expert level knowledge in how to do various things. So we have a wide range of speakers. And if that sounds interesting to you, if you'd like to do your very first talk and you're looking for mentorship or you're not sure where to start, feel free to reach out to me. I would love to get you sorted out and maybe have you as a guest. So with that, I will hand things over to Fabian. Fabian, thank you so much for joining us today. I'm really excited to have you here. I'm a big fan of your content. So yeah, over to you.
Okay, then thank you for the introduction, and I'm going to continue with my presentation. So my name is Fabian Mosch. Most of you probably know me by the aliases, namely Secure the Shit or Shit Secure on Twitter, because yeah, my usual name is nearly nowhere to see. Only somewhere hidden on the blog post, or maybe if you saw my LinkedIn post or something like that. But yeah, that's me. The agenda for today is that I'm going to present, or I'm making a short, who am I, so what am I doing currently, and what is my position and stuff. And then I'm going to do a short introduction on why should we talk about this stuff at all. Then I'm going to talk about general approaches for evasion. So how could you in general, try to get any payload which is known malicious, or which is just a hacking tool, which is more or less a definition for known malicious, on how you can get some payload like this to work. Then we're going to talk about a little bit about environmental keying, which is already one potential Packer feature. So this is all around a Packer and the features which a Packer should have to get the best potential evasion. Then I'm going to talk a little bit about evading userline hooks, namely by unhooking direct syscalls or by blocking AV or EDR DLLs. And afterwards, I'm going to go to present some stuff about other useful Packer evasion capabilities, namely bypassing AMSI. So my favorite bypasses to still get around AMSI and or ETW, for example. Afterwards, I'm going to talk a little bit about entropy and on how to defeat entropy-based detections. And in the very end, I'm going to show a demo of my private NIM/syscall Packer, which is sponsorware, not public, which will also not be published, and just to show all these concepts more or less embedded in a single project. Yeah, to start, I'm going to start with who am I and introduction. So most of you probably have seen these, or those who already know me have seen this squirrel image. My name is Fabian Mosch. I'm currently team leader for the pentest / red team at Artec Cybersecurity, which is a cybersecurity only company based in Germany. I have around about 7 years experience in pen testing and red teaming in the moment. And yeah, my focus at work and what I love to do there is break into company networks and escalate privileges there, move laterally, and of course afterwards improve the security of the corresponding environment by giving recommendations and such. And what I'm doing in my spare time is scripting, writing blog posts, and doing Twitch videos, which landed on my YouTube channel. These were also mainly AV evasion topics somehow. Yeah, why is that? Because in my work, I was always facing environments where I had to execute specific payloads, and I'm not the person that ever says, okay, please, dear customer, could you disable this antivirus or EDR or whatever for me to execute my payload? So this never has happened, and I always wanted this to never happen. So at some point, I had to dig into AV EDR evasion, which is also therefore one of my special interests since yeah, namely from the very beginning. In the beginning, it was very different than it is now. In the last 2 years, it got really heavy. But yeah, I was always really interested in leaving as less traces as possible in an environment, staying in memory, and making less possible the most, or what it was the right, not that many alerts at all in an environment. That was always a goal for me. Yeah, I also published some repositories on GitHub, like WinPawn, Sharp Impersonation, and Pipepaster Hash, Multipotato, PowerSharphack, and several ports for different techniques or tools in NIM language. If someone is interested, you can take a look later on or whenever at my Twitter profile or YouTube channel, on my private blog post or LinkedIn profile. Yeah, introduction, AV EDR evasion. Why should someone at all try to find AV EDR? For some of you, this might be obvious because you're also working in a similar position than I do. So from my point of view, research in the infosec sector has led to many different attack vectors and public tools or POCs in all the years. Nearly everything that was innovative, that was good, that was cool in all years was published at some point after research. All the Kerberos-based attacks in Rubius, all the ADCS attacks, and so on, and all the corresponding tools. And we as pen testers or red teamers definitely at some point need to execute these tools in a target environment to get an overview and to also show the customer impact about vulnerabilities, and to demonstrate them and or simulate an attacker which could also execute these. So we as pen testers or red teams adopt these techniques and tools, but the same also goes for threat actors. So threat actors also adopt these tools and techniques, and they also use all stuff that is published at some point on GitHub or on any other channel. And as both sides are using that, it's obvious that AV and EDR vendors start to flag everything that's getting flagged, start flagging everything that is published at some point, because they don't want the threat actors and also the pen test or red teams not to execute stuff in the environments. One thing that is important to mention is that the detections for these public tools and techniques have, from my personal point of view, and I know many other people that say the same thing, has drastically increased in the recent few years. Mainly due to EDRs, I guess. And now that these detections have increased, we are not able to execute our payloads anymore. So we need at some point to use evasion techniques to still execute these known payloads and to still be able simulating attackers. I'm also often facing the situation that customers expect us or my team, my company, whatever, the project manager to evade their systems, and they would never disable a system or something like that. They definitely say to us, okay, we would like to know if you are getting detected by us or not. And this obviously is also the reason for any red teaming project. It makes no sense to disable anything there. So we need to do our job. We need to use AV EDR evasion techniques. One more thing which is just important to mention from my point of view is that just because we are evading an EV or AV or an EDR product, this means by far not that we are not getting detected. There are many more important infrastructure components and stuff that could still detect an attacker in a network, like a proxy, like a firewall, like whatever else, an NDR solution, like a solution that does behavior-based analysis for all users, or many other different things, or the blue team, if they are threat hunting or stuff like this. So only because we are able to evade those systems at some point, it doesn't mean that this environment is insecure only because it's possible. It's always possible. It's just a matter of effort for the attacker. Yeah, what are the main approaches for evasion from my point of view? I would say there are two main topics or techniques to get a known malicious payload to work in an environment with an AV or EDR. On the one hand side, that's obfuscation. So you could change the code, you could change the source code, you could remove some indicators of compromise, you could remove strings and add random stuff or encrypt them. You could add trash to the code or any random other code that just changes signatures. This could be done manual or automatic. In many of my blog posts, I gave recommendations to do stuff manually, but in some situations, it's much better to do it automatically, just because you will save some time. Obfuscation can, from how I saw it in the last years, based on source code level, or it can be used for compiled binaries. And the second approach is packing, which is where I'm focusing on today. So it's basically compression or encryption of the known malicious payload and decompression or decryption on runtime, and afterwards execution from memory. The nice thing is here that I can just say there was another speaker last week or the week before who was giving a talk about packers in general. And if you want to know about packers in general and about which code is needed at which point to execute stuff from memory, then you should definitely watch this talk, because I'm not focusing on how to build a packer in general, but instead I'm focusing on which evasion techniques should be embedded in the packer. Okay, there is a third thing which is somehow important to mention, but is completely different. So that's command and control execution. Especially for red teams, the command and control framework is really important, and they are nearly always executing anything from memory from this command and control framework. So execution takes always place from memory. But one thing which is important to mention from my point of view is that the C2 frameworks use basically the same techniques in the very end than a packer does to execute stuff from memory. It's like PE loading, it's like shellcode execution with syscalls, or it's assembly load for C# assembly. So in the very end, it's the same, but that you don't have to drop the payloads at any time on disk, because the C2 should mainly run in memory. One example for obfuscation, just so that you get a better overview of how that could look like, is I obfuscated Rubios here with logic.net and disassembled the, it's not disassembling, it's decompiled the code afterwards to see the difference. On the left-hand side, you can see an unobfuscated as a wrap roast class from Rubios, and on the right-hand side, you can see how the same code looks like when it was obfuscated. And you could see, for example, here that all the strings are visible on the left-hand side and the strings are not visible on the right-hand side anymore. So if any AV or EDR builds signatures for strings that are in Rubios, then this obfuscation would lead to the fact that these strings are not there anymore, and that signatures for the strings fall away, so that the binary can be executed without detections. I also added a short example here for entropy, but I will explain that later. The plain Rubios version had an entropy of 5.8, and the protected version, the obfuscated version, had 5.0, so the entropy for the obfuscated version was lower in this case. The plain Rubius version had 56 detections out of 70 on virus total, and the obfuscated version had 39. So I would definitely say this is a public obfuscation tool. This is not the really best result that you can reach. And I would say this is, on the one hand side, due to the reason that this obfuscating tool is public. So vendors are building signatures for this obfuscation algorithm. And you can see that from the descriptions from the AV vendors. For example, you can see here that GData scores the plain version as Rubius A. And if you see the obfuscated version, it's still flagged, but it's flagged with a generic signature. And this generic signature is, my guess, is some signature specifically built for obfuscated C# assemblies, or maybe even dedicated for this specific packer. So many signatures fall away, or some signatures fall away, but others, and these are highlighted here, are just different signatures, though the vendors started flagging the obfuscator itself. Or it's about generic detections. Yeah, this just as an example. From my point of view, public obfuscators, especially the public ones, in the case for C# assemblies, lack important IOC changes or capabilities. For example, they lack the functionality or the feature to rename classes, namespaces, or functions. They lack the feature of changing the GUID, or they have bad string obfuscation. They use base 64 or road 13, and these can easily be still flagged by AV or EDR vendors. The obfuscation itself often leads to new detections. The entropy may increase. In our example, it decreased because there is more randomness. And there are no more plain strings visible, which makes the assembly or the binary more suspicious, and this can lead to generic detections, as we saw in the examples from the two images. Also, obfuscation needs you to, in many cases, adjust the tool or adjust the obfuscation for the tool or for the payload. It may work for one tool, but another tool may be broken if you're using obfuscation. And obfuscation should always be used for multiple languages or for multiple payloads in multiple languages, C#, C++, C, Go, Nim. So there are many different examples here, and also on GitHub for offensive security. Yeah, this is some downsides from my point of view for obfuscation. In the example for packing, I took the Nimcrypt packer from GitHub, which is public, and I also obfuscated Rubius. And you can see on the left-hand side, because we cannot decompile the assembly or the resulting binary because it's written in, or nim compiles to C, and we cannot decompile that, we can only disassemble that. But this is an hex editor here, and you can see that there are some few strings, but you will not be able to see any Rubius related string in that resulting binary because the packer uses encryption. So you will never see any part of the payload in the resulting binary because it's encrypted or compressed. In this case, it's encrypted. Entropy comparison. The packed binary has an entropy which is much higher, 7.8, and the plain version has 5.8, so the plain version is lower. What this is about and why this is important is shown in the entropy section in this talk. We can also see that the packer is using some additional, or has some additional features. In this case, it has sandbox checks, keyword environmental keying. It's applying an MZ patch, and it's also applying an ETW patch. And then after doing that, it decrypts the payload and executes that from memory. Just to see the difference, it was 56 detections for the plain Rubius version. And for the packed version, it was 12 detections. In this case, the packer is relatively new, so I guess the detections will definitely increase in the near future because it's public. But there is a big difference between the packed and the obfuscated version. And you can also see here that this is only generic detections. There is not a single vendor stating that it has detected Rubios. They did. I took a look at the same sample on VirusTotal 1 day later, and it had 30 more detections. But that's because they did more and more checks afterwards in the sandbox, and they found out that from memory scans or whatever, that Rubios was unpacked. And then they flagged it 1 day later. We can also see that the entropy in one specific section, the R data section, is very big, but in the other sections it's low. I'm going to go a little bit faster through some points because I'm not really sure if I make it 45 minutes. I thought I had like 60 minutes, so I'm going to hurry at some points. Yeah, packing still has some problems, especially public packers will get flagged because everything that is public is flagged at some point, as I mentioned in the very beginning. So if you're using any public packers, if they are new, this might be fine because you can use them and they are not getting detected that fast. But after some time,
Hey, Fabian?
they will get detected.
Just to interrupt you. If you need 60 minutes, by all means, go ahead. Don't feel like you need to rush through this and skip over things that are important. Just do what's comfortable for you. Okay.
Okay, fine. Okay, so building signatures for any public tool is easy. So it will definitely result in signatures if you publish anything on GitHub or anywhere else. And one thing that is important to know for packers is that most packers have big parts of the loader, so the resulting binary, are the same for any payload. So if you're packing Rubios, or if you're packing a Cobalt Strike beacon, or if you're packing whatever, the resulting binary will look equal in the very end for all payloads because it is the same code. The decryption routine is the same. The decompression routine is the same if you're doing that. The evasion features are the same. So it's also easy for any open source packer to build a signature for every single resulting binary. And if you have a signature which flags one resulting binary, then you can also flag all others because they all look the same at some point or equal. Also important to know for the packing approach is that using any defense evasion technique can lead to additional detections. So if you're applying an ANSI bypass, it is possible that your payload or the loader is flagged on runtime just because you were using an ANSI bypass, but this depends on how you did it or which one you were using. If you're patching ETW, it's also possible that your binaries, in the moment when you do that, is flagged on runtime, behavior-based, and that you will not be able to execute just because you are using that. Same for unhooking, same for direct syscalls. Any of these techniques can potentially lead to additional detections, but this, from my personal experience, mainly depends on how you implemented them. Then detections by entropy. This is also a thing for packers, especially for packers. If you have large payloads, you will have a really big entropy, and this leads to detections. But why that's the case and how to get rid of it, that's somewhere in the end of the talk. Yeah, we also had C2 execution as one example for payloads. There is not that much to show. I just made a short example for, in this case, Covenant, and executed Rubios from memory. And because nothing is on disk from the payload, the only thing you could see the payload is by doing a memory scan and by looking at the memory. So I, in this case, dumped the PowerShell process memory and searched for Rubios and also found that. So in C2, or for many C2s, not for all, but for many public C2s, your payload will still be visible in plain text in memory if you didn't obfuscate the payload before. Yeah, for C2, I also wanted to mention some things for that. Any open C2 framework or open source C2 framework, it's also easy to build payloads for that. And that's the same reason for packers and the same reason for obfuscators, because it's public. This is I bought a book, hacking AV Hacker's Handbook, I guess, and the very first sentence in this book was, everything that is public is flagged. If you write your own things from the very scratch, and if you don't use any code which was used before, you're perfectly fine. This is the best evasion you can do. So, and it boils down to that for anything. So anything that is public will get flagged at some point. The initial C2 stager, this is the thing that you need to usually obfuscate or pack to get around an AV or EDR. So anyone who's using C2 frameworks builds some shellcode or whatever, and this is typically embedded in a packer, or it's retrieved on runtime and executed from memory to not put it on disk anywhere. Yeah. Some C2 frameworks, or more and more, are using memory encryption. So in these cases, you cannot even see something in memory anymore. And one important thing that I just wanted to mention is that obfuscation can lead to a memory scan bypass, but packing can. So this is also a downside of packing. If you are obfuscating, we stay with the example of a C# assembly, you could also execute that with a C2 with execute assembly or whatever, and it would not get flagged by AMSI because it's obfuscated. But if you are packing an assembly, and if you run that and the memory scanner is done for that process, it will be found in plain text without any obfuscation if you didn't do that in combination. And a packer typically does not anything to the memory region, and therefore packers are flagged, but obfuscated binaries are not flagged from memory. Or they sometimes, it depends on the obfuscation, they can still be flagged, but obfuscation can lead to a bypass of memory scans. Yeah, there are also behavior-based detections for C2 execution. Reflective PE loading, this is one thing that we're also doing with a packer. Assembly load is one thing that we're doing with a packer for C# assemblies. PE loading is to execute any PE, like Mimicuts, for example, from memory. You need reflective PE loading as a keyword for that. For shellcode execution, this can lead to detections, memory scans, also for C2 frameworks and so on. But I didn't want to dive too deep into this C2 thing because the main focus should still be on a packer in this talk, from my point of view, and this was also my goal. Yeah, and now we're going to talk about the very first, from my point of view, important feature that a packer should always have before basically doing anything. So this is also the first thing, because I would say from what a packer does, in which order, environmental keying is one of the very first things. So AV or EDR vendors tend to upload any samples that you put on disk or that you put on any system in a target network. They tend to upload that into the cloud, into some sandbox environment, to directly check the behavior of this payload. And if they find some malicious behavior, they will instantly delete your binary or block the execution or prevent. And block prevent is the same. I could have deleted that. Yeah, and but what could we do as attackers to avoid these behavior-based detections in a sandbox environment or in a cloud? We can, before doing any evasion features, before decrypting the payload, before executing the payload from memory, check the target environment to see if it's clean or if it's potentially a sandbox. We can do that before, that's what I just said, before retrieving the payload, before unpacking, decrypting the payload, before doing memory execution. By doing that, we will also slow down the incident response process, because if any blue team finds our binaries which load something from memory, or persistence binaries or whatever, they first, if they want to analyze it, they also may put it into the sandbox, or they maybe make an analysis, and the very first thing that they see is some checks, but not actual decryption or anything else. Yeah, if you already know some things about the target environment, and if you already know some facts about this environment, you can do for example, stuff like checking the domain name. So you could say, I know that my target environment is using the internal domain example.net. So I'm checking for, is the current system joined to the domain example.net? And if you say it is joined to this domain, then you can make the evasion features, decrypt the payload and execute it from memory. And if it's any other domain, or if it's no domain at all, then you just execute something completely different, something that is not malicious, or you just exit. You could also, for example, check the Active Directory user count. If the system is joined, you could say, I know my target company has 500 employees. I could say, okay, I want to have a minimum of 500 Active Directory users in an environment before doing anything else. You could check the time zone. If you know your target company is based in Europe, you could say, I would like to check for Europe time zones. If it's something else, don't execute something malicious. If you don't have environment information, you could check for a domain join in general. You could also check for, because many sandboxes or cloud systems are not joined to a domain. And if you say, I'm checking a domain join before decrypting and doing anything else, and it's uploaded to the cloud, and then your payload will not get executed there, and the cloud cannot do a behavior-based analysis. You could also check the disk or memory space, because many sandboxes or cloud environments have really low disk space or not that much memory. So you could say, I would like to have my target system to have a minimum of 500 gigabyte of disk space, or a minimum of 8 gigabyte of memory. I would like to have my target system a minimum of 4 processors, for example. Or you could also go and check, for example, the browser history. So user activities. You could say, or you could check, does my target environment and the user that is executing this binary already visit 50 or more URLs in the last week or 2 weeks? Or did the user in the environment where I'm executed open more than 25 documents in the recent document counts folder? You could also check for that. And there is one link here, which you can visit if you're interested in that, where many different examples are. But I'm also giving more links with many coding examples, which are all public, so that you can also get an overview from the code or of the code on examples to actually also get an idea on how to implement that in your own Packer or in your own malware. Also something really good, or which is from my point even better than the other checks we had before, is okay, message box click, for example. On the right hand side, what we see is a small PowerShell example, which is just popping up a message box, and the payload will only get executed if the user clicked on OK in this message box. And a sandbox typically has no user activity, so a sandbox would not click on a message box on OK, so it would not get executed in a sandbox because of that. You could also check if the mouse clicks several times, or if the cursor position changes in a specific amount of time, and only if the mouse was clicked like 20 times or more, then the payload is executed. This can be after, in a real environment, this could be after 30 seconds, but it could also be after 5 minutes or after 2 hours. But as an attacker, you don't really care if it's executed directly or after 2 hours, not necessarily. So this should be perfectly fine for you. But in a sandbox, there is no mouse click usually, so it would not be executed there. Window changes, I think this is not self-explanatory. This is something that Mr. Unicoder, namely Charles, showed me at some point, but I think it's really cool. It's you can check if the current window on a monitor has changed a specific amount of times, and only if that window changed, you will execute the payload. For example, I have now a PowerPoint presentation open, and if I open up the browser, this is one window change. If I open up Notepad in front of it, this is another change. And if you say, if something that is presented on the monitor has changed 7 times or more, then the payload is executed. If there is no change at all, then nothing is executed. And I already said that I'm going to provide you the opportunity, at least, to take a look at code examples. And the ones that I personally like the most in this area are located in these two or behind these two URLs. So the check please repository is really cool on GitHub, and it also has many of these examples that I mentioned here, but not only in one language, but I think it's in 5 or 6 different languages. And the checkpoint evasions project is a really good overview. I think the most examples there are in C or C++. So if you're interested in that and to get more examples, you could definitely, or you should take a look at those links. Okay, then I'm going to talk about evading userland hooks. But first I would like to explain what they are about. So AV vendors or EDR vendors are typically using userland hooking for their, I quoted that, behavior-based detections. Somehow it is behavior-based detections, but from my point of view, somehow it's also not. Or it could look different, or I'm expecting something else from behavior-based detections. But they are using userland hooking. What is userland hooking about? On the left-hand side in the image, you see the syscall ntcreate section from the MDLL Windows library, and this is the clean one, so the unhooked one. This is how a syscall looks like typically if you're viewing that in a debugger, or if you're taking a look at the ASM code. If you decompile MDLL, you will see the same. This is just how it should look like. And on the right-hand side, you can see a hooked function. And hooked in the very end means that there is some jump, some modification in memory. And in the case for AV or EDR vendors, it's a jump to the EDR or AV DLL, which is typically loaded in any new process. So if you start any process, and if it's anything which later on unpacks malicious shellcode, for example, then the ER will, when the process started, it will hook any or many different important functions, and it will place a jump to its own code to be able doing an analysis for input arguments for these Windows APIs. And if this analysis results in a known malicious payload, it will kill the process because it says, okay, this is malicious. It's doing some stuff on runtime which I don't like. I'm going to kill that. And to get a better understanding for this, because when I first heard that and when I first was faced with these things, I found it really hard to understand personally. And maybe it's a good. So I'm thinking I'm going to provide an example on how such a detection could look like. So we are going to use an example for the MDLL function ntcreate thread x. One very simple vanilla shellcode runner that someone, or that you will probably find in many different offensive security tools or C2 frameworks, especially older ones, is the usage of the Windows 32 functions, which are on the left side here. So we are opening a process with the open process function. We're getting a handle to that process. Then we're allocating new memory with, for example, virtual alloc X to have a specific new memory region where we can place our shellcode into. then we're using write process memory to write the shellcode into this newly allocated memory region. And afterwards, we're calling create remote thread to execute the shellcode, which was written into the newly allocated memory region, in this case with a new thread. And what's important to know is that create remote thread will call in the very end before the execution takes place, it will call nt create thread x from the ntdll function. And on the right hand side, we can see a definition, an example definition for nt create thread x. And we can see that there are different input parameters, a thread handle, the desired access, the object attributes, a process handle, and for example, a start address. And the start address is exactly the thing where an EDR and AV vendor could take a look at when it's executed, because this is the address where our shellcode is located after doing the things from the left-hand side. With write process memory, we wrote it to exactly this address. And when we call create remote thread, it is in this address and it is in clear text. So the EDR vendor will do a jump to its own DLL and will check the input parameters that were used for nt create thread x. And it will, especially in this case, maybe check the start address to see what is going to be executed here and what is it. And they could, for example, apply Yara rules on that memory region to find known malicious payloads, for example, Cobalt Strike beacon, a Sliver beacon, Covenant shellcode, or whatever else. And if they find such a signature in clear text in this memory region at that time, they can directly kill the process, or they will directly kill the process, because then they know, okay, there is something malicious. Okay, this is an example. I hope that makes it better understandable for you. And now it's on us. How can we get rid of these detections? So one example on getting rid of these detections is to use unhooking. And unhooking is the process of grabbing a fresh NTDL copy from, for example, from disk or from known DLLs or from any location. It could also be from a remote web server. And the file on disk is typically not hooked. It's not manipulated by the AV or by the EDR vendor. They only manipulate in memory. So if you grab a fresh copy from disk, it's not hooked. You can then search for the current process and TDLL text section, because the text section is the one that contains executable code, namely all the functions that are typically hooked. And then we are going to override the text section of our current process and TDL memory with the text section of the newly grabbed NTDLL. This means that in the very end, and this example here is from the offensive NIM repository, the unhooking example. If we do that, then we, on the right-hand side, you see it's hooked, and we're taking a new fresh copy, which looks like the one on the left-hand side. We are using this content and overwriting the content on the right-hand side, so the right-hand side looks clean again. And then no jump takes place at all to the EDR DLL. And when no jump takes place, also no analysis takes place. And if no analysis takes place, then they can also not find our shellcode and kill our process. So this is one technique which could be used. Then another technique which I personally prefer, like all of the time, is to use direct syscalls. So we are not only retrieving, for example, a fresh copy of NTDLL, but we are also directly putting that into memory and executing that from memory, so that we are not going to unhook the functions in our own process at all, but we are putting a new copy, or we are building a new copy of the syscall in our memory process region and executing it from there, so that we are executing the same code, but not from the text section which is hooked, but from a different region in memory. And this could be done, or they could be retrieved from memory. This is all the gate techniques that were published, like Hell's Gate, Tartarus gate, recycle gate, and there are many different other gates. But in general, you can say that the NTDLL or a specific part of the NTDLL function is retrieved from memory, from the current process. And with this specific part, you can build the whole syscall and execute it directly. The second famous option here is to use, I called it get syscall stub here because, yeah, for reasons, many functions are named like this. This is grabbing a fresh NTDLL copy from disk instead of doing that from memory. For example, the deinvoke repository from the UVA, which is in C#, is using exactly this technique to grab fresh syscalls. I also ported that to NIM, so I have a public NIM port for this technique in my GitHub. Or you could, as a third alternative, use embedded syscalls. So there were 3 different versions of this Whisper so far. The first version had the whole syscalls embedded in the binary. The second version retrieves only a part of the syscalls on runtime, and the rest is embedded in the binary. And the third one is a heavy one, which makes crazy jumps and obfuscates the syscalls, and they come from NTDLL and not from another stack when they are executed. So there is many more different evasion features in version 3. So this is more or less the options that you have if you want to execute direct syscalls from my point of view. And the example that you see here is from this Whispers version 3. And you can see here that nearly everything of a typical syscall is completely embedded in the code as ASM, but only the syscall number is retrieved on runtime with a specific function. And I think this was also the jump code, so but I'm not really sure. I have to look it up. Yeah, but only a specific part is retrieved on runtime, and the rest is already embedded in the binary. They all have advantages and disadvantages. It would also be possible to do a talk for each of these with 45 minutes or 1 hour, but that's way too much for this time. So I'm only going to tell you which options you have from my point of view, and this is these 3. Then there is another technique to evade userland hooks, namely MDLL blocking. At the moment, there is only one. I know only about one repository and technique which is doing that, and the tool is SharpBlock. The blog post, the corresponding blog post from CCOP is linked here on the bottom. And the technique is that the binary itself will create a child process, so a new process. It will create a new process, and it will register itself as a debugger for that newly created process. And the debugger can retrieve debug events from any other process that it's debugging. And in this case, it's checking especially for the load DLL debug event. And if that appears for the EDR DLL, so the process initially only created in suspended state, I guess, and then it started and debugged, and the execution stops in the moment where you receive these events. So the EDR will not be able to fully load when the process is created, but instead you have the option as a debugger to do some actions in between. And in this case, it's waiting for the moment when the EDR DLL is loaded, and it's patching the entry point of this EDR DLL so that it looks, as an example, like the image on the left-hand side here from the blog post, that the entry point is executed, but the entry point is then only returning true. Means the DLL is loaded, but then the DLL is directly exiting and not doing any analysis at all. It's not creating any hooks, and it's not doing anything else, but it's just exiting, and therefore the DLL will not appear in memory and cannot do any analysis. So that's the technique. But I can highly recommend you to take a look at the blog post, or it's 2 blog posts, and also about the code if you want to know more about that. There will be a new technique similar to that, but somehow also different, which I found in the recent months, and that's the one with the shellcode that I mentioned somewhere in the beginning, or it was not recorded at that time, but I plan to release one more technique this year, which is somehow similar with the same effect, but it's also blocking EDR DLLs. Yeah, how could these evasion techniques or direct, no, how could all of these evasion techniques for userland hooking be detected? There were many companies that released these techniques, and they also stated it could be detected this way or that way. And hooking, for example, this is something that I had in my head, hooking could, from my point of view, easily get detected if the EDR would check regularly if the hooks were removed in some process. So an EDR could just go and check, are the hooks still there? And if they are not there anymore, then the EDR knows, okay, unhooking has taken place. I'm going to kill this process. For direct syscalls, an EDR could check if, for example, file read for NTDLL on disk was done. So did the process retrieve a fresh copy from NTDLL from disk? And if yes, that's potentially malicious because it's potentially using direct syscalls. An EDR could also check if the syscall in the stack came from NTDLL or not. If you're using direct syscalls, or many of these techniques are not jumping into NTDLL, but instead are directly executing that. So if an EDR takes a look at these memory regions, they will see that they came not from NTDLL, and they could also say this is suspicious and or block it. For the DLL blocking technique, from my point of view, an EDR could check if the DLL was successfully injected or not. And if it was not injected, it could say, okay, I'm going to retry. And if it's not possible again, then I'm going to kill the process, something like this. But I have to say, although many people state that these detections could be there, I personally never faced any of these detections myself. Maybe I just faced the wrong EDR products. I cannot tell. Maybe the false positive rate is too high if they implement these detection techniques. I cannot tell, but from my point of view and from my experience, this is mostly theoretical detections. Maybe it applies for very few vendors, but I personally didn't see them so far. So yeah, it's up to you about which technique to choose. Useful packer evasion capabilities. Now we're going to talk about AMSI and ETW. So depending on which payload you're executing, your packer should definitely use an AMSI bypass. AMSI detections can occur for C# assemblies, for PowerShell scripts, for JavaScript, for VB script, for VBA macros, and only for that. So if you're executing or packing any shellcode, or if you're packing any portable executable, then you will not need to execute an AMSI bypass before. It's just not needed because AMSI is not able technically to detect shellcode or to detect portable executables in memory. It's only for the payloads from above. So you should always have in mind when to use or enable a bypass or not. For many payloads, you may not even need an AMSI bypass. One technique, and that's the most famous one to evade AMSI from my point of view, is just the plain old patching or hooking of AMSI scan buffer or of any other function from AMSI DLL. So we could call load library to load AMSI DLL into our process memory and to get a handle. We could then call get process address to get the address of the AMSI scan buffer function from memory. And then we could change the memory protections to read-write. We could copy patch bytes into the specific region to change the behavior, and afterwards restore the old protections. And the goal for these techniques is to break the functionality of AMSI so that the analysis will never take place, for example. So if you're in this case here, I think it was just putting a return statement into AMSI scan buffer. So AMSI scan buffer is called to make an analysis. and if we're patching it, then just return is called and an analysis takes never place, and for that reason also nothing malicious is found. But this technique, especially if you're not using any syscalls, is really often detected in the meanwhile, because on the one hand side, EDRs check for the integrity of MDLL functions memory in the meanwhile. So they are checking actively, was something patched in the address space of MDLL, namely for scan buffer. Was there some manipulation done? And if yes, they are killing the process. I faced those detections personally, and I didn't say that till now. Most examples that you saw here were not using direct syscalls or unhooking. And this code here that you see is also not using syscalls, but I can only highly recommend you to either unhook or use direct syscalls for any evasion technique that you are using. If you're not doing unhooking or direct syscalls, then it will get catched anyway. So it's highly recommended from my point of view to use syscalls here, and there are different examples already on GitHub on how to scan, on how to patch scan buffer with syscalls. I also have one in my repository in C#, but also there are NIM examples and in other languages as well. Yeah. Then one thing that I personally find is less likely detected than the classic patching of the direct function is patching at a specific different offset. And in this case, it's an example also from Mr. Unicoder. There is the offset of 83. So we are not patching directly at scan buffer, but instead we are patching scan buffer plus 83. And this is a different position in memory. And because it's a different position, these integrity checks, which I just mentioned, which check the exact location of scan buffer in memory, they will not find anything because the patch is not done at this location, but it's done later. And for this reason, these are less likely detected. But I would still say that there are detections. I personally faced EDRs which also flagged this offset location. But it's not that much. It's not that many. I only saw a few vendors blocking this here with a specific offset so far. One problem of this technique is that it's not compatible with the Windows OS builds, because the MDLL changes in different build versions. And for example, this patch here would not work on a Windows 11 system, sorry, but only on Windows 10. So you need to adjust the offset for different Windows versions. And I'm going to give you one hint here. If you want to know what this is about, you can open up IDA Pro. And in IDA Pro, you can put MDLL from Windows 11. You can put that into IDA and disassemble it. And then you will see something like this here. And on the bottom left side, what you see here, this is where the analysis takes place, where the potentially malicious buffer is analyzed. And before that is done, there are multiple other checks which all have a jump 0 statement. And every time when you see jump 0 or jump not 0, it's very easy to just patch that with a single byte so that a different thing is done in memory. So if this jump 0 will apply, then the analysis is done. But if we change that to jump not 0, then the right-hand side will get executed, and that results in no analysis at all. So we can patch basically any other location, any other offset, with from jump 0 to jump not 0 here, to reach a NAMSI bypass. And all these are also the same offset on Windows 10. So in the moment, you're perfectly fine to go patching any of these jump 0 statements to jump not 0, and then you have a compatible version for Windows 10 and for Windows 11. Okay. Another technique that I personally really like, because I think it got way not enough attention when it was released, is patching the AMSI provider DLL. So in this technique, we are not patching AMSI itself, because AMSI, there may be some integrity checks that will get flagged or detected. But instead, we are patching the AMSI provider. And the AMSI provider, you can check this technique out in the link on the bottom with a really good explanation. If we patch the AMSI provider, namely the function DLL get class object, we can prevent AMSI from getting initialized at any point at all. And this is nice, especially if you're doing it from C, C++, Go, or NIM, because in those languages, AMSI is not loaded by default, so it has not been initialized yet. So you can always load the provider yourself first, before AMSI is loaded. You can then patch the provider, and afterwards you can execute your payload, and then AMSI will get loaded, but it will not get initialized because the provider is patched and it will fail. One thing to mention here is that the correct provider can be retrieved from the registry. Many EDRs use different providers than the one in this example here, the MPOAVDLL. They use their own providers, but you can retrieve them from registry on runtime and patch the corresponding DLL from the corresponding EDR vendor. And that technique, I tested it against multiple EDRs so far with their custom provider. They did not flag it when I used that, but I also used it with syscalls and not with Windows 32 functions. Potentially in the future, this technique could still be detected if they take a look at the provider DLL and at the DLL get class object function. Yeah, how long did I talk already? It's like 50 minutes, right? Then, depending on the payload, you could or should also patch ETW. Detections ETW could occur for C# assemblies, but ETW can also check and find process activities, so newly created processes, newly created threads, newly allocated memory, DLLs that were loaded, or it can detect network traffic. And this is used by EDR or AV vendors to make some behavior-based analysis. And you can see if these ETW events are generated if you're opening up a process with Process Explorer, for example, from sysinternals, or with Process Hacker. And if you go into the .NET assemblies section, if you see some stuff here, then ETW events are generated. If you see nothing, and if it's timing out, then no more events are generated. In this case, you can see it's a PowerShell process, and you can also see there is seatbelt loaded in this PowerShell process, because this is one thing, or one easy to understand example on how AV or EDR vendors could detect that some potentially malicious C# assembly was loaded in the process. They see just the string seatbelt and they know, okay, seatbelt was loaded here. But there's many more things that you can do with ETW, and the repository on the bottom here, this demonstrates many different things that you could potentially detect with it. So if you're interested in that, you could visit this link and take a look at that. You should, same as for AMSI, not use an ETW bypass if you don't need it. So sometimes when I know that an EDR is flagging a specific technique, I'm also disabling the ETW bypass, because I know it's working when I'm disabling it, but it's not working if it's enabled. Yeah, there also is plain old patching. It is basically the pretty much same approach than for the AMSI scan buffer, but we are loading NTDLL and we're patching the function ETW event write. An example is here. You can take a look at it if you want at some point. But it's pretty much the same thing then with AMSI scan buffer, but only for a different library and for a different function. Instead of doing that, instead of patching the most famous function, you could also patch NT trace event. And this is, from my experience, less likely detected nowadays. So this is the recommendation also, which you should patch in the moment. Anti-trace event. I personally had one EDR vendor which flagged anti-trace event patches due to integrity checks, but all the others were perfectly fine with it. But I personally did not face all EDR vendors. I also have to admit that. But I would say this is my recommended way in the moment to patch ETW events, and then they are not generated, and when they are not generated, there is no analysis at all. But one thing, one good news, because this is getting started to flag already, I took a look at NTDLL anti-trace event, and there are also offset candidates to patch. So you don't need to patch anti-trace event, but you can also open that up in EDR Pro. Take a look, especially look for jump zero, jump not zero statements, because they are easy to patch. It only needs one single byte, and you can avoid generating ETW events by patching these offsets also. More relevant alternatives, there is hardware breakpoints to bypass AMSI or ETW. The first example was from CCOP, Jerry Coburn, I guess. You can take a look at that. Or, for example, offensive hooking to block DLL loading. There is one example from this blog post, which I personally also like, because it can also be used from NIM, C, C++, Go, and so on, because AMSI is not loaded yet. If it's not loaded yet, you can just hook these functions which I mentioned in the blog, and it will not get loaded at all then. You can fully prevent AMSI from getting loaded. And the hardware breakpoint is, I guess, the recommended way in the community in the moment, because it's not patching anything at all, and not any function at all, so there cannot be any integrity check-based detections by AV or EDR vendors. But I personally just didn't, it's on my agenda, but I personally just didn't implement that in my tooling so far because I had no need for it. I was perfectly fine going with patching offsets or by hooking or preventing DLL loads. I just didn't need it so far, but I will definitely take a look at that, and I will also implement that in my Packer in the future. It's on the to-do list. So we are also going to talk about entropy, at least a little bit. Entropy in the very end indicates the randomness within a specific set of data. That means the more randomness you have in a data or in a file, the higher is the entropy. And especially for Packers, this is important, because if you have a really big payload, like if you have a Go binary with 8 megabytes, and if you encrypt that, and if your loader only has like 50 kilobytes, but it decrypts an 8 megabyte payload on runtime, then there's a really high entropy, because 99.999% of the whole executable are just random data because it's encrypted. And there is a really cool case study. I really like this article, so I can recommend you to read that, which stated and made an analysis over many different executables and samples, and for an entropy from 5 to around 6.4 or 6.8, the number of good samples were higher. So malicious samples are the one that are red in this graph, and the good samples, the non-malicious samples, are the green ones. And you can see that the higher the entropy is, the more likely is it that this executable is malicious, because it's most likely packed or something like that. The payload is decrypted on runtime and then executed from there. So many AV or EDR vendors tend to just prevent the execution of an executable if the entropy is higher than a specific amount. So if it's higher than 7.4 or 7.6, then any executable is instantly blocked when it's just dropped on disk. And to avoid these detections, we could, for example, add dictionary words into our executable. So we could take the English dictionary with all words from English and just put them as an array into our executable, because that leads to leads to less randomness, because words are not randomly generated. Or you could, for example, add zeros at the very end of the binary. That does not break the functionality at all. But if you add like 1 million, 2 or 3 million zeros at the end of the binary, then the entropy will decrease, and also the size will increase. Increased size is always, or sometimes, a good way to avoid AV or EDR detections. If it's big size, so if you're going 100 MB or bigger. You could also not use encryption at all, because encryption increases the entropy, but you could, for example, use Pokemon encoding, which is a really cool idea. There is a blog post about encoding shellcode as Pokemon names, or you could use UIDs or IPv4 addresses or MAC addresses and get the corresponding shellcode bytes on runtime back. So these are examples which should result in a definitely lower entropy. You could also not embed the payload at all. That's one thing that I personally like. You could put the payload in a separate file and load it on runtime, or you could retrieve the payload from an URL. This also has the advantage that if your executable or DLL is analyzed in a sandbox or in a cloud, the payload cannot be executed in any case, because it's not there. Only the executable is uploaded and the payload is not in it, so it will never lead to a detection, because it will never get executed at all. And the separate file will have a high entropy, but if a text file has an high entropy, it will not get flagged by an AV or EDR, but for an executable, it is. Okay, one more thing to mention, and then I'm nearly finished. Packer output formats. General recommendation from my side: try to use DLLs instead of executables. So your packer should not only be able to generate executables, but you should also be able to generate DLLs, because for executables, many more things are done, and many more analyses are done. But for DLLs, it's not. And you can load DLLs with run DLL32 or other Windows binaries, and they are signed, and in general, it's more trusted. So this is, I guess, one reason that DLLs are less likely flagged. One recommendation: you can, as a feature, for example, provide service binaries with a packer, so that you could also do persistence, or that you could do lateral movement with those. You could add DLL side loading or DLL proxying into a packer, so that you're not only generating DLLs, but you could also load these DLLs with other signed executables if they are executed. That makes an even better evasion. Yeah, this is about output formats, and now I think I already spend a lot of more time than I initially planned. Can I still do a demo, or is that too much, and should we go in questions section?
So I have time if you do. I understand, because of time zones, that it's late for you. I want to be respectful of your time based on what we agreed with. So it is entirely your decision how long you want to go here.
It's perfectly fine for me to. I will not do much. It's a short demo.
Let's do it.
Just to see. Oh, seems like my VMs were, for some reason, cut down. I did present too long. Okay, do we got a listener? Yes, we got a listener. Or it's just the wrong box. Okay, no, it's the right one. Yeah, so this is my syscall loader. And if you see, or if you take a look at the help section, you will see that there is, in the meanwhile, there is really a lot of options. You can have different output formats, like for example DLLs. You can say, I don't want to bypass ETW, I don't want to bypass AMSI. I want to be able to reflectively load my binary from memory. I want to make my payload big, like for example, oh no, this is a different one. But the things that I mentioned here were, on the one hand side, DLL generation. So this is one nice feature, to have the option of generating DLLs instead of executables. Then side loading. This is also possible with this packer. You can also generate CPL files with this packer. You can sleep for a specific amount of time to avoid memory scanner detections, and this sleep is not Win32 sleep, but instead it's doing calculations. Then you could sleep in between to avoid other behavior-based detections. So at some important steps after creating a process or after allocating memory, or in specific situations, you can again sleep. You could do unhooking here. You can do, okay, you can use LLVM obfuscation for the resulting binaries. You could pack your payload with SGN before encrypting it. There is the AMSI provider patch, which I mentioned, which is patching the AMSI provider. I also have anti-grade section hook here as an AMSI bypass. 1, 2, 3, 4, 5, 6, 7 different sandbox evasion checks. So this is the environmental keying part. You could say, I want to check the disk space, the memory space. I want to check window changes, which I explained. I want to check if the system is domain joined in general. I want to check if it's in a specific domain with a specific name, because I know that one. You could pump the binary. This is for entropy evasion by adding English words, or by size. There is also size. I just didn't put it into the help section, seems like. Oh no, this is reputation is just a different dictionary, and the third one is size, which is pumping the binary up to 100 megabytes. You could self-delete after execution, so that the executable is not on disk anymore. I also made some POCs for memory encryption, but I think from my point of view and from my experience, it should not really not be up to the packer to do memory encryption, but it's better to do that from the C2 framework, because the C2 framework has more control, and it also has control over newly allocated memory. So I recommend you to let the C2 do memory encryption and not do it with the packer. Syscall retrieval. This packer supports all methods that I mentioned. It supports Hellsgate. It supports this whispers. It supports get syscall stub, which is default. You could create a new process and inject into that. You could inject into existing processes. You could load portable executables, assemblies, or shellcode. So all three are there. And you can also, and this is relatively new, generate PowerShell output. Everyone says PowerShell is outdated. No one's using PowerShell. I'm still using PowerShell, and this payload, which is generated here, is not flagged. Is not flagged by AMSI, and it's perfectly fine. It's creating a thread, but the thread is for the NIM binary, and the payload is still encrypted. So on thread creation, there is nothing suspicious. Yeah. Okay, so this is only a short introduction about what features it has. And for example, we could say we are going to encrypt an covenant stager grant http.exe. We are using the C# flag to say our input is in C# assembly, and we are outputting it as grant.exe. Now it will encrypt the payload. and generate a new executable, which is the loader. And now I'm copying it to the desktop because this directory here is in an excluded folder, but the desktop is not, just to demonstrate that this is not flagged by Defender. Oops. Oh, come on. Manage settings, so you can see real-time protections on, cloud-delivered protections on. I'm going to execute that grunt exe. And we can see new grunt has been activated. Just for you as an information, I did not modify the stager code at all, so this is not obfuscated. This is plain old Covenant in this case. By default, AMSI is patched, by default ETW is patched, and these are the main components for C# assemblies. We're getting our grunt connection. Hopefully we can also execute commands. This is the Covenant effect. From time to time, the Covenant database makes problems. And then the grunt stays in uninitialized mode. Although it should be properly working. Yeah, I don't want to spend that much time now, but I would need to remove the Covenant database, restart Covenant, generate a new grunt now. And this is because I suspended my VM, I guess. But I can show a different example with Metapreter. This is also not an obfuscated Metapreter version, but instead it's just plain old unobfuscated Metapreter. And we have one Windows 11 system here. People told me that the detection in Windows 11 got much better than it is in Windows 10. I didn't test that much on Windows 11 so far. This is a Packer-generated Metapreter payload, which packs shellcode, and it's not patching AMSI, it's patching ETW. It's using direct syscalls to execute the payload. And the secret sauce in this case is just to use an DLL, because oh, really? Or did I put a sleep in? Maybe I also put sleep in 10 seconds. Demo effect. It's funny, I tested it just today and it worked.
Don't worry, I believe you.
Yeah, you should know it because you have access to the
Yeah.
but this is really bad demo effect. I don't like it. Okay, but I cannot do that much now. I would need to troubleshoot or restart the C2, and
Yeah.
I don't know what's the problem. To be honest,
Don't sweat it. We can just move on to the QA, and in case anyone's
yeah.
wondering, I'm sure there are a bunch of people in the chat that can confirm it does in fact work, and it works really well. So.
Yeah. I'm sorry. No good demo for today. But I guess it's the network connection. Okay. This system has network. But in this case, it's the covenant broken. Okay, but I'm not going to. I have other videos, by the way, for the Packer with working demonstrations. They are public and they are on YouTube, so if you're interested, you can just watch those instead. Yeah. And if you don't want to get access to some private pack or whatever, for whatever reason, I can recommend you to take a look, for example, at PESOR or Nimpact from Cas van Koten, or Nimcrypt, which is also linked somewhere in the slides. Before I wrote my own packer, I used these, but I used them. PESOR, I used that with modified source code. So I changed the code so that it was still not detected, because the public version typically gets detected because it's public. Okay, questions?
So before we jump into questions, I just wanted to say thank you for coming out today. That was super, super interesting. And yeah, that's great. So I'm going to read out maybe some questions from the chat. I haven't been looking at the back scroll, so I don't even know what's going on in here. Let me just back up a bit. So we have a question from Kumo. What are your thoughts on evasion by spreading the work across multiple binaries or processes?
By spreading what over multiple binaries or processes?
Spreading work.
I don't understand the question, I think.
I believe the question means, like, what are your thoughts on tasking out different components of, like, your agent or your binary into different processes? So kind of breaking up responsibilities into different binaries or processes. And Kumo, you can like chime in the chat if that's it. Yeah, he says exactly that's it.
Yeah, it's interesting. I never heard of anyone doing that, and I don't know on myself any C2 or something like that that is using this technique. So this is something I never heard of before. So I was already also not thinking about that so far.
Okay, so another question from Enter the Mat. Is Covenant your go-to C2?
No, it's one of multiple options for me in the moment. I always used 3, 4, 5 different C2 frameworks, and I used nearly all of them when they were released and just tested them out. There was a time where many frameworks were released. So I know about differences between nearly all of the public ones, but in the moment we're using 3 different ones, mainly at work. We are using Brutratel, we are using our own internally developed C2 framework, and we're using indeed Covenant, but if we're using that, it's with obfuscated changed source code. So it's a combination of those mainly, because yeah, so the self-developed C2 is basically for initial access or for any situation in which you are sure that there's a heavy detection and you just want to have your initial payload executed like with 100% possibility that you also get your connection back. For this is the internally developed one. Yeah, Brutratel is just the switch from Cobalt Strike. I personally tried Cobalt Strike for 1 year. So I don't have that much experience with it, but I really did not like the fact that I had to develop my own user-defined reflective loader. I did not want to dig into that, and for this reason I said, okay, we are not that deep into Cobalt Strike. We can also just skip that again. And yeah, open source alternatives are always good. I was always using Puppy for a long time, and I was using Empire for a long time. I really liked Empire, but I didn't dig into the newest changes yet, because there were many changes again in the last 1 or 2 years.
Awesome. One more question. How do you do direct syscall on WoW 64?
Yeah, that's a good question, because that is something where I had many headaches, and where I went through many articles where I was thinking, what the fuck is happening here? So there is approaches like Haven's Gate, which are really crazy, and you're switching the architecture mode, I guess, and then you're calling the syscall from the other architecture. But to be honest, in the Packer, it's not 100% functional to now. I started with that, but it's still not fully working, because that's one of many to-dos that I'm currently on. And I think the easiest way to make this possible is to use SysWhispers 3, because it has built-in WOW64 support, and if you're using that, it should be fine. And it's the easiest way, at least. Otherwise, you should need to switch to something like Haven's Gate. But then I also talked to other people in the community, which told me that Haven's Gate is not usable anymore at some point because of some Windows updates. And yeah, so there's some things also for me to dig into still.
Okay. We got a question from Virus. Have you run into EDRs detecting PEB walks? Any tips for evading those checks?
I think Sentinel-1 is doing that. Or it's at least obfuscating the PEB. So if you try to... so my Packer by default uses deinvoke, so it's by default parsing the PEB to retrieve functions from DLLs, and with Sentinel-1 these always crash because the PEB is obfuscated, and in that case for Sentinel-1 you could, on the one hand side, there are articles on unhooking the PEB, so you could for example unhook the PEB so that it's clear again, but I think what you mean were detections on the behavior of walking the PEB, right? I didn't face that. The only thing I faced, and the people that were using my Packer, is Sentinel-1 with the obfuscated PEB, and it's just crashing then. But in this case, and that's also on my to-do list, because there are many things on my to-do list, and it's nearly endless. This is also one thing which I wanted to dig in, is unhooking the PEB again. There is one nice article, but I would need to look that up. I don't know from mind the URL now.
Okay, one more question. So would it make sense to directly pack MDLL or whatever I need in my payload, put it in a variable and then load it during runtime, or do I run into problems depending on OS version if I do that?
Yeah, that is definitely a problem, because NTDLL changes on different Windows OS builds. So you cannot just use some NTDLL version from some system and try to execute it on another one, because this DLL changes with patches, and if it's not the correct one for the correct Windows system, then it will not work and you will have crashes. So this is not an option. But what SysWhispers 1 did, and what the other SysWhispers are doing, is they have, because all this calls look equal in big parts, they're only looking for one specific part of the syscall. The rest is already embedded, and they are only retrieving this one part, completing the syscall in their own process memory, and then executing that. So this is the way to go if you want to embed them.
Okay, so we're like super over time. I'll take maybe one or two more questions if you don't mind, Fabian, and then I think we can wrap this up.
No problem for me. I have some time.
Okay, cool. So there's another question from DVZ or DVZ Danny. How far to go with kernel callback? And I'm not exactly sure what that question means. I don't know if there's context around it, but maybe if you want to elaborate, we can take that one.
Yeah, I think with kernel callbacks, the thing is, everyone says that they are heavily used and that they flag many specific things. But I think I personally only had detections which were based on that for payloads such as for Cobalt Strike. I was in environments where I was using direct syscalls. I was using all the techniques that I mentioned here, and the payload was still on initial execution, it was still flagged even before it was executed. And I guess these were the situations where kernel callbacks were used, so where the EDR already checked that a process was headed to a process was opened, then memory was allocated and thread has to be created. And then they analyzed this memory section, found Cobalt Strike, and killed the process. But I have to say, with other payloads and the same EDR, I had no problems. So this is my personal experience. So when just using any open source C2 with obfuscation, it was not detected by the same product. So I think it is definitely a thing, but it's not a thing that matches for all payloads and all executables in the moment.
So you had a question in the chat, and it was something you touched on before. You started your talk today. It was, how do you like NIM over Rust? I see a lot of offensive Rust right now. So what's your take on that?
Yeah, I talked about that already, I think, before the recording was done. I also see that a lot of people like Rust in the moment, but I didn't try it out myself yet. I don't have an endless amount of time, especially not in my spare time. I have family and stuff, and I didn't dig into Rust yet. I'm thinking about doing that at some point, just because it's hyped in the moment, and I would like to see if that's for a reason. But till now, I didn't do so, and I really just like NIM in the moment. I'm fine with its libraries, with its syntax, and I don't see a need or a reason to change the language now, only because everyone is hyping a different language. I think that's my personal opinion. Everyone should use that language where he or she is most comfortable with.
I think that's good advice. I'm going to wrap it up here. Thank you so much for coming out tonight. This has been super fun to watch you speak about what you've been doing with AV and EDR evasion. Hopefully you'll come back sometime. That would be amazing. Maybe we could do a deep dive into one of these techniques, some live coding or whatever you want.
Then I know that I have to make some fewer slides.
As you like. Okay, so I'm going to end the stream. Thanks everyone for showing up.